This is good. This is less than I think I could do that. But it's good. Um, I don't think that girl. I mean, I did backstone work. I think you do it around 2 years actually. I didn't do it too. So like any of the other I had
Hey, I hope everyone's doing well. What I hope to do, I hope to accomplish two things today. One is I want to finish our discussion of diodes and try to understand why they operate as one-way valves for the flow of charge. And then two, I hope we can kind of preview what we're going to do in the lab tomorrow as we start the final project. So let me remind you about what we discussed about semiconductors and doping. We imagined a piece of solid silicon where there was 4 valence electrons for every silicon atom, and they would share an electron with their neighbors in these covalent bonds. And because all these electrons were occupied in the covalent bonds, it's not a good conductor. So what we decided we would try is to replace the occasional silicon atom with an impurity or a dopant, one that's specially selected to either have one extra valence electron, and that was called N-type doping. So in that case, 4 of the valence electrons would be in covalent bonds, but then there would be one left over, a 5th one, which could detach from its host atom and move throughout the material. So this is a drawing of an N-type doped piece of semiconductor. These pluses represent the dopant ions plus their core electrons, and they have a charge of +1 relative to the silicon ions. If on the other hand, we chose a dopant that had 3 valence electrons, then those 3 electrons would participate in covalent bonds, but then there would be one missing electron or a hole, and we also viewed these holes as being able to move around throughout the material. These negative signs are the fixed ions of that dopant. Its charge is really +3, but I put a negative sign because it's a charge 1 less than the kind of native silicon atoms. And what we're going to try to do is we're going to make this device, this diode, by joining a piece of p-type and n-type material with some sharp junction here. And that's where we basically left off last time. So what happens is near this junction, the mobile electrons approach the junction, and then they find these mobile holes, and they cancel each other out. And so we have this region where we don't have any of the mobile charge, but the fixed ions on either side of the junction, they're stuck in place. They can't go anywhere. And what we end up with is a region of negative charge separated from a region of positive charge. And that's like a capacitor, right? And we know when we charge a capacitor, what we get is an electric field that points from positive to negative. And so that's exactly what happens. We're going to have an electric field that points from the positive positive charge in the n-type region to the negative fixed charge in the p-type region. And I'm going to call this electric field ED. The subscript D stands for depletion. So this region by the junction is known as the depletion region because it's depleted of the mobile charge. So we'll write down some comments essentially saying all of that. So near the junction, mobile holes and electrons recombine, leading to a region near the junction that has an absence of mobile charge. And this is called the depletion region. Okay, so the fixed ions create well, let's say create positive and negative regions on either side of the junction. And so as a result, we get this electric field that points from the positive fixed region, which is in the N-type, towards the fixed negative region, which is in the P-type side. Okay, so we get an electric field points from the positive side to the negative side. And I'm going to put my little subscript D there. So if we go look at this picture again, let's imagine an electron wanders over into this depletion region. It sees this electric field, and it's going to experience a force, right? The force on the charge is Q times E, but this is a negative charge. And so the force is in the opposite direction of the electric field, and it gets pushed back into the N-type region. So this electric field is going to prevent further migration of these mobile electrons across the junction. We could do the same thing for the holes. A hole wanders over here, finds this electric field. The force on the hole will be in the same direction of the electric field, and again, it gets pushed back into the P region. Okay, so this electric field prevents further migration of mobile charges across the junction. Okay, so fair enough. What we're going to try to do is we're going to try to write down what we think the electron current would look like in this isolated diode. So we're going to consider the electron current in our isolated diode. So right now, by isolated, what I mean is we don't have anything connected to our diode. What we'll do after we consider this case is we'll connect a battery across the diode and see what changes. Okay, so what's the first possibility? The first possibility is that maybe, these electrons are going to have some distribution of energy, the thermal energy. And some are going to be more energetic than others. And maybe some of them have enough energy and they happen to be going in the right direction that they can overcome this potential barrier. If this depletion region had some thickness, so let's call this the depletion region, and we'll give it a thickness D. So this is our depletion region. So if we have electric field ED across a region of thickness D, the voltage difference across our depletion region is ED times E. And so an electron would have to have energy, electron charge, times this voltage to cross that region. And maybe some of them have enough thermal energy to do that. So there's some leakage of these electrons across this depletion region. The same thing would be true of the holes, but for now, I'm just going to consider the current due to the electrons. We could say exactly the same thing about the hole contribution to the current. Okay, so free electrons in the N region with sufficient thermal energy can overcome the potential barrier and cross the depletion region. If you want, you could have like a little picture. Imagine you had like some balls that were bouncing around, and then the depletion region is like a little hill. And some of the balls get bounced towards that hill. They go up partially and come back down. Some of them get bounced and they actually cross the hill and go over to the other side. Okay, so this is going to be the current to the left. And I'm saying it's to the left because we're imagining, say, an electron is moving from right to left. That would actually be current to the right, but if we're saying an electron, the flow of electrons to the left is what I'm thinking about right now. Okay, it would be given by A e to the minus e Vd over kBt, where this Vd is that potential barrier that we, whoops, I think we use capital D, is that potential barrier we were talking about. This is called the Boltzmann distribution. And if you haven't seen it already, you will likely see it. Did you see it? You're doing thermodynamics. Have you seen it in 215 Boltzmann distribution? The distribution of speeds of atoms in a closed container or something like that. Yeah, maybe, maybe not. So this is the Boltzmann distribution. And you can see that as we increase the temperature, this becomes a smaller negative number, and this current would grow. Okay, so as we add thermal energy, we would have more of those electrons would be able to cross that barrier. So this is the Boltzmann distribution. Okay, so that's one contribution to this so-called electron current. But there's going to be a second contribution. So remember, we had majority charge carriers and minority charge carriers. These mobile electrons and holes are the mobile charge carriers. Are the majority charge carriers. We also had the possibility of breaking a covalent bond, which would also create electrons and holes. So let's imagine that there was an electron that was created from a broken covalent bond in the P region, and it wanders over to the depletion region, and it sees this electric field, and the electric field is just going to sweep it right across. And so we'll have some flow of charge to the right, and that's going to be due to these minority charge carriers. Okay, so minority electrons in the P region, let's say from broken covalent bonds, are swept across our junction due to this depletion electric field. So this creates a flow of electrons to the right. And so we'll call that IR. Now, so we have this IR, which we haven't written down an expression for, and we have I left. Now, if we really had an isolated device like this in equilibrium, what would be the net current in our system? Zero, right? You can't, we're not going to have an indefinite flow of charge one way or the other. If that was the case, we would have a bunch of charge piling up in one part of our diode, and then there'd be a strong Coulomb repulsion and push it back the other way. So in equilibrium with this isolated device, we would expect zero net current. Okay, so in equilibrium, the net current must be 0. And so I net is I right plus I left, which is equal to 0, which of course implies that I right is equal to minus I left, which is equal to minus A. It was e to the minus EVD over KVT. Okay, so what we're going to do next is, now that we have some kind of functional forms for the left and right current, we're going to now connect a battery across our diode. So next, let's connect a battery across the diode. And we're going to do it such that the P region is going to be at a higher potential than the N region. So we're going to connect the positive terminal to the P region and the negative terminal to the N region. Okay, so let's see if we can draw that. So here's our diode. We'll put our junction over here. What colors did I use? Let's be consistent. So orange and red. So those are our fixed negative ions in the P region, and these are our fixed positive ions in the N region. Okay, so P and N. And then we have some mobile, I think we use blue, mobile holes in the P region. Okay, I won't draw too many of them. And we have mobile electrons in the N region. And we had our depletion electric field. Okay, so far that's everything we had. So now we're going to add the battery. So I'll put some terminals on the end of my diode. And we're going to put the positive terminal of the battery to the P side of the diode. Okay, and here's the negative, and we'll call this voltage V battery, VB. Okay, well, we know that if we have a battery, it would tend to, like, if, imagine this was a resistor for a moment, then we would get a clockwise current in this direction, and a clockwise current would be driven by an electric field that's pointing this way across, if this was a resistor, across our resistor. But the same thing that happens in the diode, right? We would have high potential here, low potential here, electric fields point from high to low potential. And so we're going to get a second electric field due to the battery. All right, so the battery establishes a second electric field that opposes the ED. And so I'm going to draw that as, let's see, maybe brown, I guess. And this will be our EB, the electric field due to the battery. And what's interesting about this one is that I can manipulate how big the battery electric field is just by changing the voltage, right? If I want to increase this, I just increase the voltage a bit. I can decrease it by decreasing the voltage. And you can see what's going to happen as I increase this battery voltage, the electric field EV gets bigger, and it compensates for this depletion electric field, and it makes it easier for charges to cross this junction. The potential barrier gets lower, and so there's more charge that's able to cross the junction. So the external battery can be used to overcome the depletion electric field such that majority charges cross the junction and conduct electricity. And of course, this is only when we make the P side positive with respect to the N side. If I flip the battery, then EV would flip and it would just enhance the depletion region. And so that already tells you why it operates as a one-way valve. If I was to apply this voltage and it was sufficient enough, I could get the mobile charges flowing across that junction. If I flip the battery, then I'm just going to expand the depletion region, and there's not going to be any charge flow and no current. And so that's the essence of the one-way valve operation of the diode. But let's see if we can be more quantitative than that. So now I net is equal to I left plus I right, like before. This is I left was the majority charge carriers trying to cross this junction. So previously it was just minus EVD over KVT. So we'll start with that. So that's what we had before. But now we have this compensation from the battery, which is determined by whatever the battery voltage is, like so. And then we have I right, which was the minority charge carriers. Those ones were always just getting swept across the region anyways. And so nothing much happens to that one. And we just end up with a minus AE minus EVD over KVT. So this is from the majority charge carriers, and this is from the minority charge carriers. It stays the same. Okay. We could simplify this. We could write it in a nicer way. I have an exponential of a difference, but I could write that as a product of exponentials. And then we're going to have e to the minus EVD over KVT times e to the plus EVB over KVT. And there's a common factor. In fact, you could write this as A E minus EVD over KVT. That's the common factor. Then we have a -1 for the minority charge carriers. And what's going to be left for the majority ones? It's plus EVB over KVT. Whoops. KVT -1. All right. This thing in front of the brackets is usually denoted just as I0. And its value is going to be determined by, say, the doping level of the diode on the P and N regions, and whatever this resulting depletion potential is. It's typically around 10 to the -10 to 10 to the -12 amps. So we're talking about like less than a nanoamp, maybe like picoamp level, very small currents. And so therefore, our diode current is I is equal to I naught e to the EVB over KBT minus 1. And so what I want to do is I want to try to plot this and see that one-way valve type behavior. Okay, so we'll plot I versus the battery voltage. So I could put the battery in backwards. Let's say I flip the battery and I made the N side positive. Well, then I'm going to get a negative value of VB here, and I have e to the minus some number. And that's going to be small. In fact, if I make the battery a very large negative number, e to the minus a large number will go to 0, and we'll just get minus I naught. So out here, where VB is a large negative number, our current is going to be minus I naught. Okay, if I put in 0, so the case where there's no battery, then I'm going to get 1 minus 1 is 0. So there should be a point over here. And then if I put in a large positive voltage for the battery, then I'm going to get e to a large number, exponential scroll really quickly. So I can just forget about the minus 1, and we just would have some exponentially increasing current. And so we can draw that. That's going to look something like this. And then what we have to do is we just have to smoothly connect the two regions, and they have to go through 0. And so it's going to look something like this. And so this approximates the one-way valve. Applying a voltage that's negative results in almost no current, very little current. It's like if you had a water pipe and you put in a big negative pressure, but no water flowed because there was some kind of like flap that closed or something. But then if I reverse it, I can get basically really large flows of charge across my diode, or in the water pipe, I reverse the pressure difference and I get this massive flow of water coming out. The turn-on voltage that we talked about, or we might have called it like a threshold voltage, is something like this. So this voltage is something like the diode turn-on voltage. So this is something like VD is around 0.6 to 0.7 volts is the diode turn on voltage, or to use the language that we previously used, the threshold voltage. For analyzing circuits, we often will make a simplified approximation for this. First, let me just say that I've exaggerated this negative current here. Remember, it's like picoamps, 10 to the minus 12. So it's really close to 0. I've just exaggerated just to make the point that it's not exactly 0. So we can make a approximation to this. So we would often approximate the diode I-V characteristic as, or I-V curve if you prefer. So here's V battery. So the approximation is the current is exactly 0 until we reach the turn-on voltage, And then it can be whatever value is required by the circuit that the diode is in. And so this would be VD. And so this is the approximation we used when we were analyzing our rectifier circuit to convert an AC voltage to a DC voltage. Okay. All right, good. So that's what I wanted to do. I wanted to finish off the diodes. I'm going to talk about what we're going to do in the lab tomorrow. And next week, what we'll start with is trying to build another semiconductor device, and that will be the transistor. And we'll use the transistor to make the logic gates that we're using in the lab right now. Okay, so lab final project. And it's the analog to digital converter. What we're going to do is, I'm not going to try to explain right now how the entire analog to digital converter works. The way we're going to do the lab is we're going to break it up into little parts. If you look in the lab manual, in fact, maybe I can show you. Let's see if I can find it quickly. All right, 231, lab manual. I think I've got a picture of this circuit that we're going to build. Right, so there it is. And you can see this is way bigger than any of the circuits that we've previously used in the lab. But you can see parts that are maybe familiar. Flip-flop. We built the flip-flop before the break. Counters, we worked on the counters a little bit. And then we've got a couple other little blocks here. So what we're going to do is tomorrow, we're going to focus on these two blocks, and we're going to try to understand how they work and what they do. Then next week, we'll focus on these two blocks. We'll try to get those working. And then in the third and final week, we should have all parts of the circuits working. And we're going to try to just connect them all together and see if we can get the analog to digital conversion working. And along the way, we'll talk about how the circuit works to perform that task. So what I want to do is I want to focus on this part where we've got this inverter with a capacitor to ground and a resistor from input to output. And I want to see what that does. Okay. So we're going to analyze the following circuit. And this will be more of a qualitative analysis. You can do it quantitatively, and I encourage you to do it, but we're just going to try to understand how they work. So we're going to have an inverter and capacitor to ground, and then a resistor from the input to the output. I'll call this R, I'll call this VA, and I'll call this VB. No, I don't like that. Let's call this V out, and we'll call this V in. Just one point of clarification. You're going to build two circuits that involve things like this. This is the heart of what we're going to work on tomorrow. The thing I want to point out is that there is no signal generator connected to this circuit. You don't supply like a square wave or a sine wave or anything. This is everything that we built. The reason why we can get a non-zero output is because the inverter is powered by a DC power supply. So it's getting energy source from the power supply, and it's able to have this output. We don't have to supply an external input. So there is no external input like a function generator. That's the most common issue we see in the lab. And, even though we say it now, still we're going to see some people want to hook up a function generator to the circuit. There's nothing that you need to supply externally. So in order to understand how the circuit's going to work, we need to know one property about the inverters or NOT gates that we use in the lab. So the inverters that we use in the lab have a property called hysteresis. And all that means is that if I take an inverter, and I have V in and V out, I could construct a plot like so. I'm going to plot V out as a function of V in. And what do we know? If the input is low, 0, the output should be high. And so that's definitely true. So we know for sure that it's going to start something like this. And if I make the input high, like 5 volts, the output should go to 0. That's what an inverter does. So if I'm over here, my output should be down close to 0. Okay, and if I was to start at a high input and decrease it, eventually there's going to be a transition to a high output. And so I could do that. I could imagine turning my input down. So I'm going to turn my input down this way, and then eventually we're going to get this transition to high. Okay. I could do the opposite. I could say, well, let me start with my input low so that my output's high. So I'm over here. And then I start increasing my input. Eventually, it's going to transition back to low. But what hysteresis means is it doesn't follow this exact curve. Actually, the transition from high to low occurs at a different voltage. So as I decrease the input, I will eventually get a low transition, but that occurs at a different voltage. So this transition where the output is going from low to high occurs at, say, V1. And this transition where the output goes from high to low occurs at V2. Okay. So with that, we should be able to analyze our little circuit. So let me draw it again so that we just have it nearby. So capacitor to ground, and then resistor, and this is going to be our V out, and this is our V in, and we want to know what happens to the circuit. So V out can only be high or low. There's no other options. And so basically we have two cases to analyze. All right. And so let's assume that initially V in is low and V out is high. Okay, so we're going to assume that we have something like a high voltage here and a low voltage here. So high voltage means like 5 volts, low voltage means 0. So I could draw an equivalent circuit. I have 5 volts, my resistor, 0, capacitor, 0. If I have 0 on both sides of my capacitor, that means the voltage across capacitor is 0, and it's completely uncharged. Okay, so the equivalent circuit is, let's see, this is where my V out sits, and it's at, say, 5 volts. And then we have our resistor. If we follow the resistor, we get to V in. And we said that was 0 initially. And then we have our capacitor that goes to ground. So our capacitor is uncharged initially. All right. Well, what's going to happen in this case? What would this circuit do? We have 5 volts here and ground here. What kind of current are we going to get? Which direction of the current is going to be? Down or up? Down, yeah. So we're going to get a current I that flows down. Current is the direction of positive charge flow, and so we'll get positive charge piling up on the top plate of the capacitor and some negative charge on the bottom plate. And so the capacitor starts to charge. Okay, so what I want to do is I want to plot this as we do the analysis. And I want to have 2 plots. We're going to plot V in as a function of time. Yeah, love that. Go. And below it, I'm going to plot V out as a function of time. So what did we say? We said initially Vn was 0. And so that means our output was at 5 volts. So here's 5 volts and our output's sitting up here. Okay. Our capacitor is going to charge. Let me indicate 5 volts over here as well. Oops. So here's my 5 volt line. We know how capacitors charge. They do this kind of asymptotic approach to their equilibrium voltage. And so I'm going to draw that as a dashed line. So a charging capacitor charges something like this. The rate that it approaches this equilibrium is determined by the RC time constant. Okay, good. The other thing I want to put on this V in plot are our 2 threshold voltages. The 2 voltages I want to put on there are V1 and V2. Okay. So we'll have, let's say V2 is up here somewhere. And V1 is over here somewhere. All right. So our capacitor starts charging up. And eventually it's going to charge enough that it's going to reach V2. Well, what's going to happen when it reaches V2? Our output's going to jump to low. Okay, so capacitor starts to charge once the voltage across the capacitor reaches V2, the output transitions from high to low. Okay, so I guess we can live with that. So we would have, at this time, our output was sitting at high and it's going to drop low. So what we have to do next is we have to figure out what is our equivalent circuit when our output is low and our input is high. Or say, well, okay, let's say now we're gonna do the low and high case here, or maybe it's not high, maybe it's V2. Maybe that's more accurate, right? The transition happened when our input, which is equal to the voltage across the capacitor, reaches V2. Okay, but a low is like 0, so it's like our output is connected to ground. So what would that equivalent circuit look like? So when V in is equal to V2 and V out is equal to 0 or low, the equivalent circuit becomes, let's see. One side of our capacitor is always connected to ground, that never changes. And then the other side of our capacitor is connected to V in, and we're going to start with V in equals to V2 initially. But if the V in is V2, then the voltage across the capacitor is V2. This is no longer an uncharged capacitor, right? The capacitor charged up a bit. So we've got some charge on this thing. And then our resistor is connected to one side. Well, one side of the resistor is connected to V in. And then we set the other side at V out was low at 0 volts. So that's as if it was connected to ground. What's going to happen in this case? What's the capacitor going to do? What's going to happen to the charge on this capacitor?
It'll discharge.
It'll discharge through this resistor. Exactly. So the capacitor discharges through R. Okay, so as the capacitor discharges, this voltage V in is going to decrease below V2. And so a discharging capacitor would look like something like this, right? It's exponential discharge. So it begins to discharge, but the discharge is going to be cut off. Why is it going to be cut off? What's going to happen when we reach V1? What's the output going to do? It's going to go back to high, right? So our V in starts at V2, it's discharging, it reaches V1, and the output's going to go back to high. So the cap discharges until V in reaches V1, at which time V out transitions from low to high. All right. So there's another important time here, somewhere around here, where our output is going to jump back to high. And now we're back to the first case where the capacitor would start charging again. And so the capacitor starts charging, reaches V2, then it starts to discharge, reaches V1, then it starts charging, reaches V2, and so on indefinitely. And so at all these times where we switch from charging to discharging, the output is switching high to low, low to high, high to low, over and over again. And this little inverter circuit with the resistor and capacitor is a square wave generator. Okay, so we get a square wave at V out without supplying any input. And what allows this to happen is that hysteresis in the inverter. The fact that the low to high and high to low transitions occur at different voltages, V1 and V2. And so that's the heart of the circuits that you'll build tomorrow. Okay, good. I think we're out of time. So we'll see you tomorrow in the lab, and we'll get a start on those final projects.